There we go. Let's say I'll just say hello to everybody, and if you can hear me, say yay. See if I hit the right button. So we'll see if the chat will.
Yep, we're live.
Okay, good. Good. Yay. I didn't mess it up this time. So welcome everybody, especially our Southern Hemisphere folks that always love to, come on here and say hello. But today we have a special guest, Dr. Elizabeth Butler. She is a space weather forecaster. So we love learning about this stuff and what goes into, what makes these forecasts and how they do it. And every one of them has a little bit different of approach. And I think it's been great because every time somebody talks about it, we learn something new. So these are always fun conversations. So without further ado, I will hand it over to Liz here.
Hi, thanks. Wait, just to double check, people are seeing the slides, right?
Yes. Yeah.
Cool. Okay. Yeah, so it says Space Weather Prediction Center because that is where I was trained and where I worked for a little bit. It's an open question right now whether or not I can get to continue working there. So I figured, talked with Tanya and Mary Beth at the Space Weather Workshop in March. Oh my gosh, that was 2 months ago.
It's hard to believe.
And we were talking a lot about how SWPC does forecasting and how that relates with aurora chasing and stuff. So I figured today that I would go through two different ways in which SWPC actually does that, since it's a little bit of like a black box for people. So I'm going to go through how we go from the actual data that we see coming in through to the forecast that actually gets published on the website in two case studies. So the first is the 3-day forecast that we put out twice every UTC day. And then the second one is how we forecast the arrival time for a CME and what its maximum impact in KP will likely be. So because my link didn't work, this is our 3-day forecast, where it starts off with the KP in 3-hour intervals for 3 days, some English underneath it, the percent chance of having a proton event for the 3 days, just hitting the NOAA scale threshold and above, and then the percentage of getting an X-ray flare in the various levels for the 3 days. So there's actually not too much on there. And then this is pretty much just the numbers. If you want more discussion, the forecast discussion is an entirely different product. Okay. Share that. Okay. So starting off with the 3-day forecast, all of those things that are on that forecast, the KP, the flares, and the proton events, they all come from active regions, pretty much, which means that they all come from the solar synoptic map that you can also find online, listed under observations under the products and data tab. So that synoptic map is drawn by hand on a light box. We print out pictures and resize them to our template and then take a pen and pencil and have a lot of fun. I call it our morning Sudoku. So everyone has their own preference on which order they like to do it, and this is mine. So starting off with, you are looking at getting the sunspots on there, the active regions. So you are coloring in the umbra and then you're putting an outline around the penumbra. And you usually do that with SDO HMI continuum if you can get it. But for those 2 months where that water pipe broke in Stanford, we used gone white light images, which were not as much fun. They were very funny. I don't like them. After that, we pull up the gone H alpha image. And for that, we're going for two things. We are drawing a line around filaments and then putting little hatch marks in them so they kind of look like worms. And then also we're taking a red color pencil and coloring in all the light splotches for plage regions. Because plage is, you're still going to get activity from that, but the plage is really for predicting the 10.7 centimeter flux, which is not on the 3-day forecast, but I thought I would mention it. And then when I was making these slides, I realized I didn't have a picture of it, but the next one is pulling up GOES-SUVI data, preferably like 304 or 281 to put in the coronal holes. And those are done by drawing a circle around it and then putting little spokes inward, I guess. And then after that, and the reason you want to do the filaments first and then the coronal holes is because if you're looking in sous vide, which is ultraviolet light, filaments can look an awful lot like coronal holes, which is why you do it in that order. And then after that, you pull up the magnetic field data, again, either from SDO or GONG. Definitely prefer SDO, partly because it's much easier to see distinctions between, at least for me, who's not red-green colorblind, between the different polarities in the color than it is in just black and white. And for there, you are putting in the polarity lines as dotted lines. And this is where the Sudoku part comes in. Because you need to figure out the lines, they have to follow along the filaments, and they have to go around coronal holes. And then not only that, but you have to kind of do a lot of somewhat trajectory figuring out of, okay, this is a concentrated enough polarity that I consider it its own group. And then does it make sense with where I've drawn the rest of the holes and the other features? So this is finally over here on the right, yes, is the like 95% complete map, what it looks like. So you can see, probably not very well, but like the colored splashes, those are plage. These over here are filaments, and then this is the one coronal hole on this day. So you can see the polarities going around the hole and through the filaments, and then you have to go through and make sure that you put the correct polarities labels in the correct spots. So at this point, all the data from imagery is on there. So what you're doing in now is you're going through and making sure that the active regions are numbered correctly, that the coronal hole is numbered correctly, and also with the correct polarity. And then you're also putting in all the ephemeris data, like what Carrington longitude is going to be at the meridian, and what regions, like down here, what Carringtons are coming on and leaving, and various other steps that I've cut off here. But to go from this now to like a flare probability, we have to start doing a lot of analysis on the active regions themselves. So we now take our template from our lightbox and go over to the computer and start doing active region classification. So this is also kind of like a Sudoku, but it's more of a logic puzzle than that. So active region classification has been around since like 1960 or so. It was updated in 1998, I believe, which is why it's called the Zurich Macintosh classification, or the Zurich modified classification. I don't remember how long the magnetic classification has been around, but it's not nearly as old. And no, this has not been updated since the 90s. So in white light, active regions are classified. The first letter is basically, does it have one spot or two? And then how far apart are those two spots? Your middle number is on the biggest spot. Does it have a penumbra? And then is that penumbra symmetric or is it asymmetric? And then how big is it? And then your very last letter is, does it have any spots in the middle? And do those spots in the middle have penumbra? So like if you've ever taken a look at like our spot region summary or Space Weather Live's active region tab, those classifications will be up there. And on top of that, we have the magnetic classification, which is, okay, looking at like the magnetic polarity map. Is there only one polarity present? Are there two polarities present? Are those polarities mixed in some fashion? And is there a polarity within another polarity, and then is it mixed in some fashion? These are the best diagrams that I've been able to find for this. There aren't very many good diagrams for the Macintosh classifications. But if you would like more detailed explanations or some practice, the Royal Observatory of Belgium has a really nice page on it. But for how we do it. So taking this example from region, what is this, 4087? So this is one that's currently on the disk. So you can see we're looking at two spots. So we're looking at least a B, probably just based on my own experience here. I know I kind of zoomed in so you can't tell the length, but we're looking at largely more than a C, probably a D. I've zoomed in quite a lot. We have, so the penumbra on your big spot is pretty symmetric, but it's not terribly large. So this would be an S class, so DS so far. There are no spots in the middle of this whatsoever, so it is O or an open. So this would be, or at least me personally, because forecasters can disagree on this, I would classify this as a DSO, Macintosh. And then looking at the magnetic stuff, we have both polarities present, so we're at least looking at a beta. There's an awful lot of mixture of polarity in the large spot, but also in the trailing spot. So we're looking at probably a beta gamma. And then you can tell here you have two polarities really close to each other, and they are sharing a penumbra. So that is a delta spot. So this would be a beta gamma delta, which is one of the magnetic classifications that has the highest chance of producing a flare. So we do that for every single spot that is on the disk. And then that goes into our lovely Microsoft Access application that my software developer friends just cringe in pain every time I mention. This was literally coded in the 90s. I'm not joking.
It looks like it.
Yeah, it's... So up at the top here is where if we had any reports from the Air Force's optical observatories, they would be populating here. I happen to take this picture at a time when they hadn't come in yet, so it's empty. And then down here in the gray is what was published yesterday. And then down here is where we actually put in what we decided was going to be up. So we can look at the Air Force's information, decide whether or not we agree or by how much, and essentially like quality check it. Mm-hmm. So kind of just really quickly here, the 00Z location is the location on the solar disk that it will be at 0Z, generally the next day. So that's where you have to do a lot of math. And this is also the point where the program tends to be the most wrong. It will auto calculate that, but the sun's surface is really fluid. So theoretically, the sun is rotating at about 13.5 degrees a day, well, our day. But it's not nice and clean. It depends on what latitude you're at. Also, the spots are moving apart. They're moving around each other. Sometimes they're disappearing and more flexible emerging. So that this location has to be checked all of the time. This over here is the Carrington longitude that is associated with that coordinate point. So that also needs to be checked to make sure that that's not changing too much. The active region should always be at the same Carrington longitude, plus or minus a couple, like plus or minus 2 or 3. So if your Carrington longitude has changed by 10 or 5, then something is very wrong, or it's an entirely new region. LL, I don't know why it's called LL, but it's the length in degrees, which we at SWPC technically have no way to measure. So a lot of the older forecasters just have a lot of experience and intuition built up. So they'll just look at the picture and go, yeah, that seems relatively about this. What I will do is we pull up JHelioViewer a lot in SWPC as our analysis tool, because believe it or not, that's the only program that allows us to put a grid on the sun.
That's crazy.
But yeah, when SDO was down, GON didn't go into JHelioViewer, so I was printing them and putting a transparency over it. Yeah, it's 2025, it's fine. Right. So what I will do in JHelioViewer is I will find the coordinates on JHelioViewer and then go into Excel and do it a quadratic formula, which is not taking into account the fact that the sun is curved. We're not going to, but so yeah, that's kind of iffy. The area is the area of the entire spot. So like the cumulative area of all the spots that make up the active region. And we have no way to measure that. So we rely on the Air Force for that measurement. Though we do quality check it. Because this is where JHelio comes in really nicely, because you can do it as a movie. So you can like slide the time back and forth and see how much the active region has grown. And like you can say, yeah, no, that definitely did not grow by 500. Oh, by the way, the units on this is millionths of a hemisphere, which is not a unit that I have any particular reference point for. So I'm just like, yeah, this one is bigger than the previous one. That's always fun. Number of spots is what it says on the tin. It's the number of spots that are visible. That one is more subjective because, so one of the big debates that we have is that the classification system was developed at a time when you didn't have resolution. You just had, here's the disk, and that was it. Now we're at a point where we can zoom in and get a lot of detail. So the question is, do you do that, or is that not consistent with how the classification system was actually made? So for example, J-HelioViewer and SDO have much better resolution than the Air Force's observing network, which is on the ground, and thus subject to weather and seeing and all of that lovely stuff. So we will often say that there are more spots in an active region than the Air Force does, just because we have a different measuring system. This right here, the spot class, that's where we put in that DSO value, and it's a drop-down value. And then generally it will autofill in the mag class. So like if you have if you put in any class in there that's not an A or an H, it will automatically put in beta for you. But then we would then go in and say, no, that's a BJD or a beta gamma delta. And then the mag strength is something that we can't measure. So that is also coming directly from the Air Force, and we have no way to quality check that because. This is also the application where the active region is officially numbered right down there. And then if you want to number a new region, you go up here, say, hey, I'm numbering this region with this number. And then you have to turn over to your Air Force communication channel and say, hey, I'm numbering this region. It's now called this. And they're like, cool. Or though sometimes they'll call you and go like, why? I thought this was actually a new region, this was this, and then you have a 5-minute conversation of, no, this actually decayed and this one has popped up just quite next to it. I have had that conversation many times. Okay, so it is from partly this where you develop, or about 80% of the, what is the SRS, something region summary, solar region summary, comes from. So from these, I keep pointing my screen like you can see it, from these classifications, we then go into a different program and can calculate flare probabilities. So the flare probabilities come directly from that region classification using climatology. How often does this type of region produce a flare of a certain strength within a 24-hour period? We can adjust those probabilities based on our own intuition and the active region's flare history, which is down here. But for the most part, you don't really go below the climatology because it's the climatology, it's the average. Okay. So that climatology kind of looks like this. This is not the actual lookup table that's in the program. This is one that I made because I like my heat maps and I'm a visual person. Also, just one fun thing about this, like something that you may have noticed if you read our forecast discussions is like, yeah, so this active region is an FKC, which is about as big and complex as you can get, and it has a as you can get, but it's a very nice stable beta magnetic configuration. And when that is true, nothing happens. This is a big fat 0%. So you have to have both of them, really. And that's one of the reasons why we're adjusting the climatology up and down. So each active region gets assigned up here a probability for seeing a C, M, or X flare. And then kind of based on those, but not really, is the % chance for seeing a proton event. So the idea is that protons will be accelerated by a flare. So the bigger a flare you get, the more likely you are to get a proton event. But seeing a proton event at Earth is dependent on being very well connected magnetically. So active regions that are on the western half of the disk or just beyond the limb are actually more likely to connect. So you might have an active region on the eastern limb that has like 90% chance of an X flare, but it will have a 1% for protons because that just via Parker Spiraler just won't hit us. So then those individual region probabilities then get combined into a whole disk probability for seeing those particular C, M, and X, and then proton events. And these are the probabilities that show up on the 3-day forecast. They're also the yes. And then from this point, the oh, hey, yeah. Look, I made an entire side for this. Yeah, at this point, the synoptic map is complete. So if you will just indulge me real quick here.
I didn't realize you traced them on the light box.
By hand?
That's
yes.
Actually really, because I thought you guys actually like you had a piece of paper with a circle on it, and you actually hand drawn it, like
Yeah.
like art thing.
Yeah, so this is there are, because of COVID and the social distancing issues and all that stuff, we started to develop a way doing it digitally, which is what this is.
Okay.
There's really only like 3 people in the forecast office who prefer it this way. The rest of us do it by hand. Me personally, because I want to have at least one point during our 10-hour shift where I'm not holding a mouse. But so, for example, so this is what the completed one looks like, where you have all your individual active regions, and then below them are their flare probabilities. So C, M, X, and then proton probabilities. And then you have your whole disk probabilities up here. So also, because the digital one, this bothers me, but there's no legend down here.
Right.
It bothers me. So actually, this is great. So in the digital one, these are active regions. This is a coronal hole.
Mm-hmm.
These are filaments, and then the rest are the polarity lines. So this is positive polarity, negative, and largely the same stuff, but it looks very different. And it looks like there's no plage on this, which could mean either that there wasn't any observed, or that data, or the data wasn't available, or they just didn't do that bit. That also sometimes happens. So going back to that. Okay. So at this point, we have 2/3 of the 3-day forecast done. We have our flare probabilities for the 3 days for all of our thresholds and the proton events for all 3 days. So for the geomag forecast, that so we do that out in 3-hour chunks per day, our 3-hour synoptic periods. So there are, I believe, 6 per day. You can do mental math, 6 or something like that, 6 or 8.
Yeah.
And the KP is a mixture of all of these things. It is the flare probabilities, because the larger the flare, the more likely you are to have a CME associated with it. If there are coronal holes and they become geoeffective, then you'll have a high-speed stream, which is not so much of a problem during solar max, but as we're going into solar min, it becomes more of a problem. And then whether or not there was an observation of an Earth-directed CME already in the works. So it is up to the forecaster to put all of that together in your own mind. There is no model, there's no algorithm that does that. The thing that's closest to that is this program, which is an IDL widget, which was also developed in the 90s, that has a little thing up here. So this is recurrence. So this is just 100% what happened yesterday or within the last 7 days. You have the physical forecasts, which are the forecasters inputting, hey, a coronal hole is this big, it'll be visible for this long. And then it just kind of has a very simplistic algorithm from that. And then you have the climatology of what has happened just in general with these types of things. Most of the time, none of us really look at this. So down here is where you are putting it, so for each of the 7 days, even though we only do 3 days, you're putting the percentage out of 100, how likely you think it's going to be quiet, unsettled, active, minor storming, major storming, or severe storming. So this is basically 0, 1, 2, 3, 4, 5, 6, 7 plus KP, essentially. And then over here at the side is not the average, but the AP value that you expect to see for that day. Because we coordinate very closely with the Air Force, and the Air Force is based on AP values, not KP. So we do both. Then once you have put these numbers into your satisfaction, you then go over here to the 3 days, and it will you can say whether or not you want to do KP as a function of AP or AP as a function of KP. Most of us choose to do this one, because then you are trying to set up your synoptic periods, KPs, in such a way that you get the AP that you have forecast. And that's a little bit of just a numbers game, and also like, okay, I think the CME will arrive at this time or within this synoptic period, so we'll start seeing things increase here. Or like these later synoptic periods, we're going into midnight, and so we're starting to see more bursty stuff from the tail, so it will likely increase slightly there. Just things along that. But it really is just kind of playing with the numbers to see what you get. And then making sure that you have a somewhat of a physical rationale behind that, but there's really more art than science in there. Okay, so that is a complete 3-day forecast. That goes out twice a day at 0:30Z and 12:30Z, which, I forget, are we in summertime?
Yeah, I can never remember. I can't do that conversion.
Yeah, because that's like at around like 6 or 5 mountain time or something. It's weird for us, but the entire meteorology world works on UTC, so we do too. So right, that is where our 3-day forecast comes from. And then the discussion goes more into why those numbers were chosen, for the most part. Okay, so that was the first case study. Moving into the second one, this first one, as I mentioned, it goes out twice a day, every single day, holidays, weekends, all of that stuff. CME arrival times only happen if there's a CME that we're pretty sure has an Earth-directed component. Like if, the NASA Moon to Mars Space Weather Analysis Office, they are responsible for space weather forecasting for all NASA missions. So they model everything around the sun because they're, forecasting for Juno around Jupiter and Psyche and Europa Clipper and all that stuff. We only care if it's Earth directed. So if it's very clear that the CME is farsighted, we don't care. And we don't bother going further than that.
Makes sense.
Mm-hmm. It does make our life a lot easier.
Right.
So most of the time, we'll see like, oh, hey, look, an X flare. And then we wait. Usually 2 to 3 hours to see if it shows up in LASCO. If it's exceptionally fast, it'll show up in about half an hour, but that's like super rare. Like, you will get like 1 or 2 a year, kind of super fast. Most of the time, you're sitting at your desk doing like, the 3-day forecast and the forecast discussion and all the other like Air Force tag-ups. And then you look over and go, oh, hey, look at that. There's a CME. It came off the sun 3 hours ago. Cool. Or you have a flare come off that the Air Force reports has a Type 2 and a Type 4 radio burst on it, and so you're pretty sure there's a CME coming, and you're waiting, and LASCO decides to have a data gap of 8 hours. That's also always fun. Because LASCO is not an operational chronograph. Right. It is also, I cannot remember, we're going to lose both SOHO and ACE within the next 2 years. By the end of 2026, we will have lost both of them. I forget which one. One we're losing at the end of 2025 and the other at the end of 2026, but I forget which one is which is why there's the chronograph on GOES now.
That makes sense.
Because we're trying to get it to cover the gap before we can get the Space Weather Follow-On mission up.
Yeah. Okay. SOHO's been up there forever, though. Like
1995.
Yeah.
Yeah, it's been up. It's amazing, honestly, that it has worked as long and as well as it has, considering what it has endured. And that it was built in the 90s on Eddie's technology. Anyway, once we have images, we're generally waiting to get at least 3 or 4 because that makes the fitting process a lot easier. So once we have the images, we go into our CAT tool, or our CME analysis tool, but it's just very affectionately called CAT. So that will pull up images from GOES C-Core, the LASCO chronograph, both C2 and C3, and then also from Stereo A. This used to be Stereo B, but we no longer have Stereo B, so it is now C-Core. And so the purpose of this is that, at least when you had Stereo B and A, they would be looking at the CME from a different angle than SOHO at Earth. So you could try and triangulate a little bit. So essentially what you are doing is you are trying to match the shape of it. So I'm just going through here just a little bit. Down here you have the actual images timeline, so you can see where do I have data gaps, and also how many images do I have to work with. So this is data that I pulled up on Friday from a filament eruption from the 12th of May that went off the, I'm sorry, this is a typo, northeast quadrant. The filament, so it started moving around early in the day on the 12th. It was visible in SOHO as erupting at the very, very end of the day. And then it became visible in the chronograph imagery about 4 hours or so after that. So pulled that up into CAT. So the first thing that you want to do is you want to find images that are taken at roughly the same time, so that theoretically you're looking at basically the same structure, just at a different angle. And then what you are doing is you are playing with these sliders down here to get, I'm sorry, it's a really thin line, but to get this little cone, ice cream cone shape to match some structure in the image. I hate how thin that line is because it's even really hard to see in the actual forecast office, and I've asked them to change the color and make it thicker. So there are many, and this is also where it kind of comes down to more of an art than a science again. What you are fitting in here really comes down to what can I see consistently in every single picture and every single instrument. Theoretically, you want to be hitting this like inner edge of the shock or the outer edge of that inner cavity because because of how WSA Enlil does the shock. There was this whole debate about whether or not WSA Enlil inputs its own shock or not. It's this whole thing. Different forecasters have their own different preferences. It's a whole thing. Anyway, so this was my first attempt at a fit where it's like looking okay. Oh wait, no, hold on. Let me double check something. Yeah, okay. Yeah. Sorry, this was my first attempt at a fit where I'm sorry, it's really hard to see, but like it's fitting, the inner edge of there in all three instruments okay. So like this is decent, and I'm sorry, this is really small, but the latitude is 65 degrees north, which is much too far north for the observations of the filament in ultraviolet images. So I'm going to fiddle with it more. And now I have a latitude at around 45, which is much closer to the UV observations. And also you can kind of see it's gotten a lot broader and it actually is fitting all of these a lot nicer. Mm-hmm. And so now we can start doing the thing where we're just playing with the radial slider. How far out does this cone go? And then once you get to a point where you like how it's fitting, you tell the program, yes, this does actually match what I'm seeing. And it now shows up in this plot down here, which has no labels. And the scientist in me has such an issue with this. This is a distance versus time plot, essentially. So what we're trying to do is get a lot of points on here so that we can fit a line to it and get a velocity.
Okay.
So you can see here that these two have been shown as fitted. And then you just go through and fit as many of these either as you prefer or as there are good images to do so. This is why we like to wait till we have at least 3 or 4 images, because fitting a line to 2 points is really iffy. You want at least 3. The more you and also the more you have, the more robust and confident you can be in that fit. Also, I prefer just having as many points as possible because, as you can see here, sometimes there are data gaps and you want to make sure that something wonky isn't going on there. Like with this stereo image, I don't know what happened there. I spent like 10 minutes trying to figure out, but like, nope, that was the image and that was the fit, so meh. Also, as you can see, there's this data gap in stereo. There's no CME in these images. And after this point, it's starting to become really faint. Mm-hmm. And also at a certain point you get earthshine in C-core, and so some images are just not useful whatsoever. So I was happy with all these lines. This looks nice and straight because yes, it's just a straight linear fit. There's no quadratics or polynomials or anything in there, nothing intelligent. And so you say calculate my velocity and it will give you a straight line. So this comes out at about 460 kilometers per second. Which was in the same ballpark as the other fits that the forecasters on duty had done, so I was happy with that. So at this point, you click the button down here that says Export Results, and then that goes into our interface with WSA Enlil, and then you can submit the run to CCMC, and then you wait for at least 75 to 90 minutes.
That's a decent amount of time.
At that point, you are either doing like a MacGyver ensemble by fitting other features, getting other forecasters to fit features, you're doing things like writing the forecast discussion, or you're eating lunch. The first day, my first day at work, I was getting a tour of the forecast center, and the forecaster on duty was like, there have been 10 CMEs today. I haven't done any of my actual work. So like, it all depends on what happens. When you finally get it back, you get really excited.
It's like, yay.
Also, and this is what our interface looks like. And also, I'm going to point out here, this is not my run. I didn't actually submit that. This is the one that was used for the actual forecast, which was, there was the potential for a glancing blow yesterday, with impacts probably minimal, which is pretty much what we saw yesterday. So you have, like, these are the parameters that came from CAT within. This is an image to say what, so that you can see what fit was used. And then you have your NLO actually results. I noticed in your CCMC stuff from 2 weeks ago, he had also like temperature and something else on here. We don't get those. We only get density and velocity plots.
Okay.
And only at Earth and only at stereo A, though I don't know why we have stereo because. So it's from this that you forecast an arrival time. And that is also something else that is a kind of forecaster preference / debate. Do you take the middle of this rise phase? Do you take the peak of it in the density profile, sorry? Or do you take this inflection point where it starts to arrive? Like, what is arrival? And then, so you'll notice that we don't have any actual value given. It's just a time series. So WSA NLO does not actually do a forecast arrival time. It's not something that it does, which also means it doesn't provide any uncertainty. So like, NASA Moon to Mars, for example, when their time, they just automatically put ±7 hours. What we end up doing in our forecast discussions is we use like thirds of the day language, like early on the 4th, midday on the 5th, very late on the 6th, and like that type of language, which I ran a survey for an internal project for another thing. And the forecaster pretty much agreed that early means about 0Z to 9-ish Z, midday is about 10 to 4-ish Z, and then late is about like 5-ish to midnight Z-ish. But we can't be any more precise than that, and so we just don't bother. We do internally because we have bets, but not externally.
I like that.
The other thing is then, okay, so you have an arrival time. How bad do you think it will be when it hits? Again, this is not a thing that we have a model output for. There is no model, there is no algorithm. The relationship between CME and KP is really not well understood. For example, how fast the CME is going doesn't really have a relationship with KP. Having a negative BZ has a more obvious correlation, but you can also have a neutral BZ and a very large negative BY and get a large KP, particularly at the fall and spring equinoxes. So what goes into that is a lot of thinking. You're thinking about like how big was the CME in our coronagraph imagery, because that gives you at least some sense of like relative mass. How Earth directed is it? Are you expecting a pretty direct hit in that center of mass, or are you expecting a glancing blow? If it's a glancing blow, how glancing is it? Like, are we expecting just to get like literally nicked on our way by? Or are we expecting a little bit more of a stumble? How fast is it going compared to your ambient solar wind? The ambient solar wind, if you're not in high-speed stream, tends to be around 300 to 400 kilometers. If you have a CME going at 450 and the background is 400, yeah, that's like a ripple. Whereas if the background is 300 and your CME comes in at 700, yeah, that's more like a shockwave. And then also, were there any other CMEs either before it or behind it? If you have a CME, two CMEs in sequence, that first one is going to act like a snowplow, and it's going to like sweep up all of that ambient solar. The second one is so there's nothing to impede it, so it will accelerate a whole lot faster and won't lose as much momentum. And that's how you start to get CMEs that pile on top of each other, and that's what happened last May.
Okay.
Yeah, so you're looking at all of these factors and doing a lot of thinking. Also, this is not exhaustive at all. This is just the main ones. And then there's a lot of crystal ball in there of like, have you personally seen a CME in that chronograph imagery that looks familiar? And so you can make a guess that this will be similar. which I literally have had forecasters go, oh yeah, that looks like that one from this date. It's going to be big. How confident are you in your cone fit in CAT? Like, did you feel that fit was actually pretty decent? Do you think the source region was correct? CMEs can actually, or like eruptions off the sun can be deflected. There was an eruption that I saw where the eruption was here. So you expect the CME to go off that way, and instead it kind of did this down south. So your source region in CAT will not match up what your source region in ultraviolet says it should be. So how confident are you that you fit it nicely? And then how confident are you in WSA's and the ambient wind? Like, does that actually match with what you're seeing in ACE and what you expect to see from ACE? Because again, how fast the ambient is going will determine how big of an impact your CME will have. And then also, how long do you expect those effects to last? Are you expecting this to be a 1D CME? Is it going to ramp up and then stop? Is it going to ramp up and go back down? All that stuff is pretty crystal ballish or intuition experience. And then you put the two of them together. And then from all of that thinking, you go into our KP IDL widget from the 90s and put in your forecast if it's within that 7-day range, depending on things. So yeah, I was talking with a bunch of solar physicist researchers on Friday, and they were all shocked that there were no models behind anything. It was all tools and techniques. Because I mentioned that forecasters, we really prefer to have model or like techniques over models. And someone in the audience asked, but they're based on models, right? I'm like, no, they're not.
It's like,
researchers really like their models. Forecasters, not so much. All right, so that's the actual forecast, which actually turned out to be pretty decent. So yesterday, right, so this is May 17th, or it's yesterday. So you did have G1, G2 conditions on May 17th. So that's actually a pretty decent forecast. Though the signature in the solar wind isn't that distinct, you have no obvious shock. But again, we were expecting a glancing blow, so that makes pretty much sense. So this was actually overall a fairly decent forecast. For kind of a counterexample. So this is a model run from a CME that lifted off on like New Year's or around there-ish, I believe. And so you can kind of see that its time signature is much more distinct, like pretty obvious, like that's almost a step function. You're going to be like directly hit whammy. And you can kind of see from Enlil that, yeah, it's going to be a bit of a glancing blow, but we're going to be much more direct probably than the one that we just saw. Except if you look at the solar wind data, this is January 3rd, January 4th, where WMSA Enlil said, yeah, we're probably going to get hit. And some G1, there's a couple of, 4Ps, maybe a 5Z, 5O, but nah, it's not particularly. The thing on New Year's from earlier that week was much more obviously. Look at this very nice shock. We had a G4.
Yeah, that one was like legit.
Yeah, I was actually in the office that day alone with my B shift because it was New Year's. No one was in. So I came in for day shift, and S shift, the swing shift is like, you're walking into a shit show. Have fun. That was actually quite interesting because, so when you have that going on, you are, just as an aside, you're doing a lot of phone calls because you're doing phone calls on all of the alerts. You're initiating our power grid hotline. When we hit that G4, I was calling FEMA. And then I pick up the phone that didn't have a caller ID on it, and I was like, "Hi, Space Weather. This is Elizabeth." It's like, "Hi, this is so and so from the White House." I'm like, "Excuse me."
Excuse me.
What?
Yeah.
It was an aid for someone who just wanted to verify some information. Apparently, someone in NOAA had been saying this was the first G4 ever, and I'm like,
"Wait, what?"
No.
Yeah, like no.
I mean, it's the first this year.
Yeah.
Because the year just started. But it's not the first, so but that was it. It was like, yeah, this is the White House. I was like, excuse me. But anyway, yeah. So the main point of this slide was that forecasting KP off of a CME is very hit or miss. Again, more art than science. And that was all I had. Those were the two big case studies because these are the two main things that most people, if they're just coming for like general space weather, are coming for. If you have a very specific need, like aviation or or orbit determination, things like that, then you have specific products that you're looking for, which may or may not be included in those. But those are the main things.
Okay. So I had one question. It was, how does the degree of difficulty increase when you have multiple CMEs like last May? How much of that crystal ball do you use?
It kind of does both. Yeah. In the one hand, because when you have multiple CMEs like last May, so pretty much all of those were pretty Earth directed. So it was kind of honest, like, yeah, those are going to hit. And when they hit, because of that sweeping effect, and the ones behind it are able to go faster, so they're going to catch up and pile up. So in that regard, May was somewhat easy because, like, yeah, that's going to hit, and yeah, that's going to be big when it hits. The main thing is that in the entirety of solar cycle 24, there were no G5s. I think there was one G4.
Right.
So that is about 15 to 20 years or so. And so this is the thing, is that most of the forecasters in the forecast center, I think the one who's been there the longest has been like 15, 17 years. So the people who've been working there would not have seen a G5. So now you have the thing of, yeah, that's going to hit. Do I dare pull the trigger on that G4 plus, forecast? Luckily, someone did, and they were right. But forecast-wise, for what makes it difficult, the ones that are coming directly at you or directly away, those are really easy. It's the glancing blows that you're just like, because you're staring at it going, well, it could, it might not, and then like, kind of, particularly because you are basing this off of a cone fit that is, it's the best thing that we have, and it's amazing how well it works. Literally, I think most of the globe uses CAT in some fashion. But it is also, you are putting a 2D shape on a 3D structure and then doing a linear fit to get a velocity when it is definitely accelerating. And then WSA, though, like, it's great. It's a wonderful model, and it is also a model. And then there's also, the point of what we're discovering that CMEs have a lot of internal structure. So it's also like, what bit are we going to get hit by really kind of determines things. So I would say it's not so much how many long story short, it's not so much how many CMEs as the geometry and orientation of the CME that you're seeing.
Yeah, I could see with you describing it, like, even with us when we talk about these glancing blows, it's like
yeah, it's and there have been studies done that people get more anxious over an uncertain outcome than they are of a negative outcome that is certain.
Yeah.
So it's
pretty crazy. Yeah, I noticed in the Janelle in the comments, like, yeah, how last solar cycle was just so quiet. So like, to not even get one G5 out of it is like,
well, and the thing that I find fascinating about that is, right, the amount of space and technology innovation and then also software innovation that happened in that time. And people are launching their satellites into space and have, whole systems and industry that's dependent on having that satellite data, and they have no idea.
Yeah.
That the sun has weather that they need to pay attention to.
I mean, what, like yesterday or last night when the big debate online was this Steve that showed up, but was actually a Chinese a rocket launching satellites. I'm like, oh, good, they're launching that into a geomagnetic storm. That's cool. It's like
yeah.
I know Starlink did that once and it didn't pan out very well for them, but then again, every geomagnetic storm is different too. So like, I don't know if you looked or read into the Starlink incident, but there was a very sharp turn in the BZ from like south to north, and then that caused.
No, I hadn't heard that.
Yeah, it like caused it, like a flywheel. It made it like have to stop and turn the other direction, and that causes a lot of heat. So.
Oh yes.
So even though that was a G1, it was more detrimental to that particular set of satellites. So
yeah, that's kind of my theory with this as well, because we had forecasted a G3. And then we had this negative BC that, was quite low. This is about like negative 20. And then all of a sudden it went, which was right at the end of a synoptic period, it's like the last 30 minutes.
Uh-huh.
And we do have an application, I don't have a picture of it, but we do have an application that will calculate the average KP minute by minute. So we're not just looking at the 3-hour boxes. So that we can alert when things happen. And those last 30 minutes, like he was doing a steady climb, 5, 6, 7, and then but because it had switched going north there. But because of how our KP is calculated, the bucket empties every 3 hours. So it started back from 0 and then it just never got that high.
Yeah.
So
I know there's some talk about redoing these scales a bit. Because so
there's many things with the NOAA scales that are being revised right now, such as the language that's used, some of the criteria, even some of the structure of the scale itself. Like not all G5s are created equal.
Mm-hmm.
A Carrington event and last May are both G5s, but one was much bigger than the other.
Right. Yeah, it's like it's kind of like the like in meteorology, like the tornado scale and hurricane scale, like it tops out here. But and that's it. Like you can have varying degrees of an EF5 tornado, I guess, but that's like the top. So it's kind of like I guess it's sort of similar.
Yeah, and also space weather by virtue of many things is developmentally very behind terrestrial weather, partly because they've been at it longer.
Yeah.
And also I think there's some cultural differences. I had one of the older forecasters tell me that he thinks that like CME forecasting is where severe thunderstorms were 50 years ago.
I believe it.
Essentially. Yeah. Which what was it? Oh yeah. So right now, the way that we talk about our forecasts, it's all very phenomena based. What is the sun doing and what will that do to Earth? And we're moving in, you can talk to Sean Dahl more about this, but we're moving to a more impact based communication, which is a little bit more what like the hurricanes and stuff are doing, is like they're trying to move away from wind speed and start doing other things that are more impactful. So we want to start looking at more like, forecasts that are more actual helpful for decisions, decision support type services. But again, talk to Sean Dahl more about that because he's the one who's kind of spearheading that.
That makes sense. Okay, so we got a couple of questions now.
Okay.
So in the forecasting, do you take into account coronal holes and higher wind speeds when you're doing that? I'm assuming so.
Oh, like when we're doing, yes.
Yeah.
So yeah, because if you have a coronal hole, a high-speed stream, and a CME is injected into the middle of that, if your cat fit says that the CME speed is 450, but your high-speed stream is at 600, then it's just going to be swamped by your high-speed stream, and you're not going to get anything anyway. Yeah, kind of like having your signals swamped out. So this is the point where we're making sure that you believe the ambient WSI envelope run. And so that you're injecting the CME into basically what we are observing right now, because that would be how the CME is actually propagating through space. That's a long answer. Short answer, yes.
Okay. And then kind of another one, has there ever been a storm so big that a glancing blow caused a G4?
Ooh. I don't know that off the top of my head. I wouldn't be surprised. Yeah, so like we have, one of the products that we put out is a weekly summary on Sunday.
Mm-hmm.
And all the entities that eventually became the Space Weather Prediction Center have been putting out a weekly summary since 1951. And we have all those. That's kind of like my baby project. They're all hard copy. And at least 3 shelves, I'm pretty sure, are nowhere else. So I'm doing a lot of archive in my free time because I have an inner librarian. So I can't tell you about whether or not it was a glancing blow, but I can tell you that of historic G5s that we have records for, about half of them came from multiple CME events. As far as we can tell, you didn't have a coronagraph until SOHO went up. So when you're going through the historical records, you're going, okay, How big was the flare? Did it occur, 2 to 3 days before the geomagnetic event was observed? Was there a type 2? Was there a type 4? Like, was there a filament that disappeared in H alpha imagery, stuff like that? So, it is some guesswork, but yeah. One of the other forecasters put together an entire catalog of historical G5 events because she was doing a presentation on it, and then asked me to check to see how many had come from multiple events. So of the about 2 dozen or so that I checked, about half came from multiple events.
Okay, yeah, that
I
makes
can do
sense.
that.
Because I'm trying to think. I mean, I could look it up now because there was that one oh, right around the Halloween storms of 2003, with that when that big flare off when it was off the west limb, and then ended up causing a geomagnetic storm here. Like it was like November 3rd, but I don't think it was. I think it was G3. Like I think that's the highest it got. But
Yeah, and I
that's the one that
suppose
comes off the top of my head.
yeah, and to also to answer the question,
Yeah.
it is also like, yes, there could have been, or there may be one that's big enough, but also if we happen to hit a part of the inner structure where one of the magnetic components is really far south and we're at the right time of year for it, yeah,
Yeah.
that's perfectly reasonable.
So yeah, maybe.
Mhm.
And then I guess all right, so we got how come sometimes fast solar wind pushes a CME to be faster and other times it can just cancel it out?
Oh, okay. So I'm not an expert in this. My background's in solar flares, not CMEs. Um, but my gut reaction is to say ion pickup, where so like yeah, like the solar wind is both and CME is kind of generally behave snowplow like, where they're piling up the things that come before it. But you can also have, I don't know if there's a good analogy for it, like conveyor belt like behavior, where or just like, by dropping something into a stream and the current just kind of picks it up and you accelerate a little bit. That can happen. You have to have the right confluence of conditions.
Okay.
So it's not cut and dry. Although for the most part, rule of thumb, if the CME is going slower than the ambient solar wind, we don't bother with it. And I wasn't doing forecasting for very long, but I haven't seen it accelerate too much.
Yeah, what you're saying kind of makes sense. So I get that. And then this one kind of goes with like the stuff with NOAA. It's like do you think Swipsy's gonna lose certain decrease in services because of the budget cuts? I giggle because yeah, we all know
so this is the thing. I'm going to preface this by saying, so yes, I was one of the 880 NOAA employees that was let go for being probationary. I am hoping to be hired back, so I'm going to be somewhat circumspect. I can tell you that right now SWPC is at 50% vacancy. So yeah, we do forecasting 24/7. There are 10-hour shifts. They are 7 days a week, including all holidays. I worked Christmas and New Year's. So there is day shift and then day shift's backup, which does the same hours. There's evening shift, there's night shift, and there's M shift. And I can tell you right now that M shift is not being staffed.
Okay.
We have 8 forecasters and 10 shifts. They're not being staffed.
Yeah. So that answers that question.
Yeah. For the most part, I would say, the M shift is new, like as of this year, I believe. So there shouldn't be too much of a change. But yeah, like if they lose one more forecaster, you're going to start having a lot of overtime. And yeah. But I'm also very much hoping to be hired back. So
I hope so too.
I love this job so much.
I mean, it seems like a really fun job. Like, really. I just watching you talk through this stuff. I'm like, oh, that's pretty cool.
It is so much fun. Although I am going around all this going, why don't you have labels?
Yes.
There were so many graphs in my training. It's like, what's this? What and why? And then because all it said was it was one of our IDL widgets for proton events. It just had an input box labeled integrated flux. Like, cool. Whose flux is that? It's like, oh, it's the goes X-ray. Okay. Which channel is it? Oh, it's the long one. Thank you. Where do I find that number? Oh, you guess. And me, the researcher, just blue screens. Like, you want me to guess the integrated area under the curve when the curve isn't finished? Yeah,
Like, yeah.
I had many interesting moments, but I also, I mean, stressful calls from the White House aside, there was so much fun with this job. Even to the point where, like, during that New Year's Day storm, when I was doing phone calls and really busy and, doing that nervous humming singing to yourself that we all do,
Yeah.
like, I didn't feel tired afterwards. I didn't feel drained. I didn't feel exhausted. It was more like that was a good day of work.
That's cool.
Like, I feel fulfilled.
I like
So,
that. It's
yeah.
good to have that at least once, I think, in your life.
Mm.
So, let me see if there's any. Let's see here. He goes. I don't know, I'm just sorry, I'm reading questions. So it's like, oh yeah, so like if a CME that's there, how could there be a CME that's not Earth directed, but a coronal hole high speed stream could potentially push it towards us? That's kind of going back to like the deflection.
Yeah, again, every CME is individual, so they don't all accelerate at the same pace, but generally, when they're very close to the sun, like 2 to 3 to 5 solar radii or so, they're accelerating very fast, which is why we don't use C2 for cat, we use C3.
Okay.
Because actually, yeah, seeing like this is a nice straight line. Sometimes if you include C2 in there, you'll have a little bit of a curve down here, but which throws off your final velocity because curves aren't taken into account in cat. It's just a straight line, which means that your fit is more like this.
Okay.
So it would be a wrong velocity. But yeah, most of the time, I mean, NASA Moon to Mars this is their bread and butter is CME analyzing. So they are much better contact. But for the most part, most of those deflections happen in that close bit to the sun. After you get into like the solar wind, at the point, like when that point in the Parker spiral where the solar wind becomes solar wind, at that point, you are pretty much just doing the inverse inverse squared law, where you're just kind of expanding. You're not really doing too much moving around. You're just moving out radially and expanding.
Okay. That makes sense. Yeah, because it's so like what we're seeing in the imagery is like that's pretty close, obviously pretty close to the sun. So like you see it like deflect down, but if you look at it in the coronagraph there, it would be past that deflection.
Yeah, and like the metaphor that is used a lot in the classroom, not that there's much space with their classroom, but there are some, is like the sprinklers that will shoot a little bubble and they move around in a circle.
Yeah.
Kind of. It's like that, where like the main source is spinning, but the water's moving in a straight line.
Yeah, okay, yep.
Or like the individual bits of water moving in a straight line.
I always like that analogy because it is kind of, it pretty much is the
it's the closest
spiral.
we can get,
Yeah.
kind
of. Well, that's good. Oh, yeah. I think this is the $1 million question that we all wish was possible was,
sure.
can a CME polarity be predicted precisely?
No, absolutely not. At this point in time, there is no way to determine CME polarity until it hits L1 and we observe it. There are multiple people who are working on it because it is a well-known need in the community, but no one has been able to prove it in an operational setting. I think it's all pretty much proof of concept still right now.
Yeah, as I think a couple people did a paper on it because you can look at it on the sun, but you just don't know how that's actually going to arrive here from the sun. So that's like the big problem.
Really, the easiest short-term solution is actually somehow to put a spacecraft closer than L1 to the sun. And there's at least, I think, one group that's working on that with a solar sail, because a solar sail would be able to maneuver the spacecraft such that it stays relatively stationary.
Okay.
Because the thing with L1 is it's a stable point gravitation wise, because of geometry. It's the point, right, where the gravitational field of the sun and the earth kind of cancel out mostly. That's the one that makes sense. There are 5 of these Lagrange points, and like Lagrange 2 makes absolutely no sense. Neither does L4 or L3. Geometry is very strange. But putting any type of spacecraft that's along the Sun-Earth line stably, that's further than L1, you have to have it have constant altitude adjustment because it doesn't have a stable point to orbit around. And I think there's some proof of concept being done with a solar sail for that.
Yeah, because that would be way helpful.
It would be so cool. It would be so nice.
Yeah.
There was, I think, in October, on our Slack channel with all the various other space weather groups around the world, someone had shared preliminary, like, do not publish plot of solar orbiter data.
Okay.
That was much closer, but it also wasn't on the Sun-Earth line. It was like 18 or 20 degrees behind Earth. So, but we were all doing the things like, okay, well, let's assume that, like, what if it was on the Earth-Sun line? If it's seeing that type of, BZ or in BT, what would we see just on, basic magnetism principles? And then we all had bets. To see if we would get it right or not. I had like 4 sheets of scrap paper. But, the solar orbiter just happened to be in a really good spot, and we happened to have a Slack channel where they were able to actually put that up. And that's also assuming that we're hit by, as it would expand, that the part that the spacecraft saw before L1 wouldn't expand past the line, the Earth-Sun line, geometry. All of this is geometry.
Well, that's good to know.
Not my favorite math.
No. I mean, and I gotta say, it's like I'm not very good at math to begin with, so the fact that, I'm trying to...
Oh, yeah, no, I mean, I say this every time I do a public science talk. The best, particularly if it's like K through 12, the best I ever was at math was January 2018, because I did my comprehensive exams then, and it's just been a steady decline since.
I mean, what they say, if you don't use it, you lose it, right? And then, and then you have
I haven't needed to do vector calculus and differential equations since I was in fluids.
Yeah.
I do spectroscopy.
And
I do way more stats.
And then you have like the NO model stuff. You plug it in, and it does it all for you, right? So
yeah, that's another thing. Is I am an observer by choice and training. I have never developed a model in my life.
Yeah.
So
kudos to them, because I couldn't do it.
Yes, computer science is somewhat black magic to me.
Yeah, same here. So, and then Janelle asked what your degree is, and it's in solar physics, right?
Yeah, so what I tell people is, so my PhD is in astrophysics, but I don't do astrophysics. So if you want to start a fight at the American Astronomical Society,
good.
You go around saying that solar physics is astronomy, and there will people who will fight you on that. Because yes, the sun's a star, but the data regimes are so different and the pots of money are different that yes, people take offense to the idea of solar physics as astronomy. So yeah. So my degree is in astrophysics, but it's solar physics space weather based. And my bachelor's is actually a double. I went to a really small liberal arts college, so I was able to do this because my physics department was 5 professors. My graduating class was 4 people.
Oh, wow.
So I was able to take as many English classes as I wanted, so I actually have a writing bachelor's as well.
Oh, that's pretty cool.
So yeah, I've been training in writing longer than I have science, by a good decade or so. So I still look at a lot of science projects through a writing lens, which is sometimes unhelpful and sometimes is not.
Yeah, I could see it doing both, working both ways for you. Or maybe
my thought was if I didn't like research and I didn't like grad school, then I could write really nice science fiction.
Right, I was gonna say you could just jump right into science fiction writing.
I did look into freelance science journalism, but then freelance sounds really scary, so
it is.
to do that.
Not gonna lie, it is, because I've been often toyed with that idea, and it just scares me too much to do it, because you're always hunting for work, basically.
Yeah, and it's just like, no. That was the other thing that I really liked about SWPC is so I did do the traditional route of a postdoc after grad school. And the research, research as a community has, or an industry at this point, has become to a point where you can't get a professorship, which is what success is defined as, unless you have at least one postdoc, but it's more helpful to have two or three.
Oh,
Which means you are job hunting every 2 to 4 years. And not only that, but you're moving sometimes across the globe. I was in Northern Ireland.
oh wow.
So, and a good number of the postdocs there were like, yeah, this is my sixth postdoc. I'm like, what? You, so where I liked SWPC, I planned to be there for the next 2 decades at least, and have stability and security. And that's all I'll say on that.
I understand. I understand completely. Trust me. Like I had it for a year and a half and got laid off. So I sympathize wholly.
Yeah.
So whatever.
Mm-hmm. I will also say, just as an aside, being an expat, the US is one of 3 countries in the entire world that does taxes based on citizenship, not where you are located. Do you want to know what the other 2 are? North Korea.
What's that?
It's North Korea.
Really?
Yeah, the US and North Korea are 2/3. The other one is Eritrea. And I'm just like, you want to be in a group with North Korea?
That's pretty wild.
You don't actually have to pay taxes if you meet certain criteria, but you do have to file them.
Okay.
And if you don't, you pay double taxes, and it's just on a post-tax salary.
No.
I just wanted to mention that because it's not something they tell you when you move out of the U.S. You discover it
Yeah, that's pretty wild.
to your detriment.
Yeah, you're like, oh
Couple
crap.
couple of questions
Yes.
in the chat. So, you mentioned earlier about CMEs or high-speed streams containing more than one polarity or components of different polarities. Can you say more about that?
Yeah, I don't have a good thing. Yeah, so it comes down to the concept of vectors, where if you have a diagonal line, you can break it down into straight, triangle lines. So there are at least 4 different coordinate systems for magnetic fields in space. It all depends on where you want to be. Like, I think the magnetosphere uses LM and N, which means certain things. So we use X, Y, and Z for our coordinates. So X is along the Earth-Sun line, pointing towards the sun? No, pointing away? Whatever. Y is pointing along the path of orbit, or I believe, and then Z is basically north-south through the eclectic plane, up and down. So the reason we care about those is because, so Earth has a magnetic field that kind of looks like a donut if you stretched one of the sides out to a tail. Except it's not straight up and down, it's tilted off to the side. Like the Earth's like rotational axis is tilted, I think like 26 degrees, and then the magnetic field is like 7 degrees more off of that or something like that. And then also, for some reason, because of historical baggage reasons, the north polarity of the Earth is in the South Pole. So the lines come out of the south and then loop around and come back in the north. So magnetic fields are basically giant introverts. They don't like to be crowded and they don't like to get bent, but they especially do not like to be crowded. They really like their personal space. So when you have two...
That's awesome.
It's really accurate. I can say this because I am an introvert. But like if you have 2 field lines that come across and they have completely different orientations and then they get too close together, they will literally break and then reconfigure so that they have their personal space back. So we call that reconnection. So because you have the Earth's field doing this, if you have a CME coming in and can't do this in a nice way, but like, and its magnetic field is pointed like this, then at least one component is completely opposite of the magnetospheres, and that will cause it to break. This is why you tend to get more geomagnetic storms during fall and spring equinox, because at that point of our orbit, we're at a point where it's easier for those lines to be in an opposite orientation. At the solstices, you tend to have a pole pointed to the sun, and it's a little bit harder to reconnect. So that's kind of fun. That's also why I said you can have a neutral BZ, but a very large negative BY. Because again, you have, this is not just this, it's this. So if you have a neutral if you have a large negative BZ, but also negative BY, then you are completely opposite. But you can also just have a large negative BY and a completely neutral BZ, and you're still going to have an opposite component, and you'll still get, reconnection going on. BX, not so much. We don't really care about that.
Right.
But BY can become important.
Oh, yeah, that makes sense.
Yeah, I have done this thing with my hands so much. It's like, I just need like little styrofoam ball and pipe cleaners that I can bend into shapes.
Yes.
It's so often.
Let's see. I'm trying to scroll back because we had.
That is a good one.
that
Why
was a good
does the
one.
size of layer does not have any bearing on whether there is CME or not, and how strong the aurora we get?
Did you say
So-
size of flare?
Yeah, I would say it's a class of layer.
Yeah, so there is actually a lovely paper, Yashiro et al. 2006, where they demonstrated that it actually is a very nice clean correlation, that the larger the GOES class, the more likely you are to have a CME associated with you. And by the time you get to an X10, there's always a CME attached. Every time. So kind of okay, so solar flares, the popular consensus for them is that it is the result of a reconnection event within the solar atmosphere. Basically, essentially, that that reconnection is you are breaking and releasing a lot of potential energy. It's very like snapping a rubber band at your sibling. That release of energy causes a lot of trapped particles in the solar atmosphere to plunge down to the surface, which is kind of like hitting the surface of the ocean from cruising altitude. You smack down and that produces light. So if that reconnection event happens to be like, let's say, mid-atmosphere, but you still have arcade loops over, then even if you have an eruption, it can't go anywhere. And it just kind of falls back down or gets reabsorbed or something. You have to have just the right configuration, the correct geometry of arcade loops and coronal loops to get something that can actually essentially escape the sun's atmosphere enough. So, and I think there might also be something in there about you need to have enough energy to actually poof off as well, which is why C flares tend to not have CMEs associated. They can. They just don't have it as much as X flares do. So for the most part, as a general rule, the larger the flare, the more likely you are to have a CME attached. It's just, if you're below an X10, it's not a sure bet. Was there another part to that question?
I think
I'm
so.
forgetting something.
Yeah.
And it's sort of two-part question.
Yeah.
So even if we do get a CME, and it's obviously more likely with X flare than the C flare, what's the relationship to aurora?
So that I will just straight up say I have no idea. Because I'm a solar physicist, I haven't done anything on the Earth since 8th grade.
Fair enough.
Well,
Yeah.
as far as aurora goes, this is sort of from space weather class.
Yeah.
It depends on the speed of the CME, obviously, because we still can get it just from the shock.
Oh, right, yeah.
But if we do not get a whole lot of negative BZ, that's going to determine.
Okay.
Well, you still get some aurora just from the shock of the impact, that initial
Oh, right, yeah, because
arrival. But then you do need some negative BZ, or at least close to neutral BZ, with very high BT. So it has to be strong magnetic field and preferably oriented in southward. To get nice aurora. You still can get some aurora out of it if it's more of a neutral. So BY does matter, but it's sort of the efficiency of energy transfer. The lower the BC, the more energy you can sort of dump into a magnetosphere.
Okay,
So
yeah.
just because there's a CME CME does not guarantee aurora. There might be something from the shock, but that's the rest of it is
I also
how it's
have
going
to
afterwards.
ask, have you guys looked at aurora on other planets?
Somewhat,
Because the
yeah.
aurora on Jupiter and Saturn are gorgeous.
Yeah.
Yeah.
Yeah, those are some pretty pictures.
Okay, just wanted to make sure because every time I do public science talks, they're always like, "I'm sorry, what?" It's like, "Yeah, and let's talk about how Jupiter has an aurora from one of its moons."
Yeah, that Jupiter has a really strange magnetosphere.
Yeah.
Oh yeah, I had my magnetosphere class. We literally had an entire unit on Jupiter.
That's pretty neat.
Hmm. And then also, if you haven't seen it, you should go on YouTube and look up Juno orbit insertion trailer because like they did like this type of movie trailer, like thriller type movie for the Juno mission. It was great. They had a lot of fun.
I will have to do that.
All
You should look up JOI trailer.
right. So given your background in
Yeah.
flares,
Hmm.
if what can you tell us about sunspots that are more flare active? So what kind of would generate X flares, and why is the sunspot we have right now, even though it's beta gamma delta, is really not doing much flaring?
Yeah. Okay. So I have looked into this a lot. And generally, the classes that will produce the most amount of flares on average are going to be your F, E's, and D's. Um, and then also your C's. Because you want a really complex looking region and you want to have the polarities mixing as much as possible. But generally not to full on gamma, where it's just kind of like salt and pepper, because you don't have any concentrated points where those eruptions could happen. So, from my perspective, so I lived in the atmosphere for all of my grad school. All of these classifications are in the photosphere on the surface. So the idea, right, is that sunspots are the point where coronal loops are emerging from the solar surface. And they're so tightly bound together that the magnetics are actually suppressing the convection of the solar surface. So it's colder, which is why it looks black. And by colder, I mean it's like 4,000 degrees Kelvin instead of 5. Uh, so the more spots you have, the more like foot points of those loops you have. And then by having those foot points move about with the convection and all the shear and stuff, it's like moving the ends of a jump rope. You know, like the middle of the loop, it'll also start to move, and that's where you start having field lines that are getting too crowded and they're getting too bent. So you want to have as complex of a region as possible, which is why you want C's. But also, you kind of want to have more flux emergence. So more, so you tend to get, more flares when a spot is growing, in size length this way, because you have, by flux emergence, we means that there are loops that are coming up underneath ones that are already there. So they're pushing up from the bottom and they tend to have slightly different orientations because they're also being pulled in slightly different ways. So you don't tend to see much during a decay phase. So anything, coming from an F to an H, you don't tend to see much. AXX can flare, but it's like, 1% kind of in whatever. I have seen it happen. I have seen flares from no spot. I've just straight up plage, quiet sun. I have seen it happen. It can happen. It's rare, but it does happen. B's don't tend to do much. C's, it's really when you start getting D, E's, and F's. But also if you have an open spot, like this, there are no spots in the middle. So that indicates that in the atmosphere, you probably have a very simple arcade structure. So even though you have this delta spot going on, again, this is also a static image, but if you were going to look at it over the day and that delta spot is really stable, like it's not moving up and down, it's not growing or decaying or anything, then that means that the field lines, the loops up above, aren't doing anything either, and they don't have any desire to change their personal space. So kind of, yeah, it's movies are so important in the forecast office. Like pictures are great and we will use them because we'll take anything we can get, but movies are really where things start to make the most sense. Did that answer the question?
Thank you. Yeah, because I've noticed that with like even the the one last year, 664, whatever it was.
Yeah.
It was pretty like it was stretching. Like you get all that shear.
Yeah, it's so much fun. It looks like I'm not a biologist, so I'm gonna get this wrong, but like, cell mitosis,
Yeah.
where like you start to see that come off. It looks really similar to that. And it's really fun to watch movies on JHelioViewer where you literally just see spots like
Right?
it's so nice. And then sometimes if they're really big, it's so it takes roughly 14 days to go from one limb to the other, give-ish or take-ish. So basically, every month, then, if it's a big enough spot, you'll see it come back and then come back around. There was one region that came back around 5 times. It was also an H spot. So it just kind of sat there like this giant pimple and did nothing. But it was always there, which is actually kind of nice because it was somewhat of a landmark.
Yeah.
Where you could see things.
It was just a happy little spot. Just chilling.
But yeah, no, flare probabilities from climatology are one of my kind of pet projects. Like this climatology here, for example, this lookup, not this lookup table exactly, but the one that's actually behind this, that comes from a paper from 2012 and it hasn't been updated since.
Okay.
And that paper in 2012 is only using 2/3 of cycle 23. So there's many questions, but 24 was a weird cycle. Is its climatology different?
Right. Yeah.
I do know of one group who's trying to update these things. But like I've been told it takes about from discovering something to completely embedded in operations takes 20 years if it's moving at a reasonable pace. And I've been told that's true even in terrestrial weather as well. So
okay. Yeah.
The research to operations pipeline is very slow and not linear, and for many reasons, but that's a rant we don't need to go into.
Fair enough.
I have many thoughts on it.
I guess we could talk about.
I have a question. Since we're talking about flares, we have seen a few X flares that fail to generate a CME. So what determines if the region's going to be flaring? And oftentimes it's sort of the same pattern that they have. It's like the X flare, high class M flare, and they're not launching anything. So flaring regions, but not CME productive regions. And we do see sort of the same pattern of the CMEs from the same region, sort of the homologous CMEs, meaning they're all look-alike. So something is deflecting south, it's going to continue to sort of rotate through the disk and continue to shoot CME south and missing us completely. Kind of disappointing, but what drives that behavior?
So long story short, we don't know really what causes an active region to flare. There are a lot of theories. There are a lot of papers looking for pre-flare signatures. But no one can tell you for sure, absolutely, or within a reliable time frame that yes, this active region is going to flare. To be honest, SWPSE would really like to have warning of an imminent flare, as in the next 10 minutes. Whereas it looks like a lot of the research community is focused on just in general, will an active region produce a flare? Which I'm not sure if that's a communication gap, miscommunication, or if that's simply where the feasibility is in the research right now. I'm not entirely sure. So when it comes to, we do know that once a region, well, I am working on this. I was going to say, having the flare history of a region has been proven multiple times in multiple different methods to improve flare prediction. And it is also very true that there are at least, like, I think in cycle 25 that I've looked at so far, at half of the regions that produced a flare never flared again.
Huh.
So, because I'm working on some conditional flare probabilities, because I want to know, is like, what's the, like, you have an active region that has produced one flare, what's the chance it'll do so again? And then will it produce higher? Anyway, so I can tell you that just because you have produced a flare does not mean that you'll do it again necessarily. And there's also a growing debate on if you produce a lot of C flares, are you simply dissipating energy and thus you won't be able to produce an M flare because that's more energy? Or are you like building up to larger and larger tantrums, essentially? So the short answer to your question is we have no idea. There are many theories, but we don't know for sure. My gut reaction is to say that if you are seeing very similar deflection on multiple Carrington rotations, then there's probably some very stable overarching arcade structure coming into it. Like a hell, well, not, I don't know about that, but
Not really from the Carrington rotation, not really on multiple Carrington rotations, from the same just rotation over the
you mean over
visible
the
disk.
14 days? Oh, yeah. No, yeah, I would still say you have some type of overarching structure that's, making that the path of least resistance. Perhaps it's a stronger field line with a stronger magnetic field, or it's simply got more plasma in it. That would be my gut reaction, but yeah, but for what causes an active region to produce more than one flare, any flare at all, and what causes that to have a CME attached, we don't know. The popular consensus, though, has a lot to do with geometry. If you look up the standard model of a solar flare, which, by the way, only works for about half of flares, you'll see a very standardized picture diagram with very standardized geometry.
Fair enough. I mean, I thought, well, yeah, I mean, you'll have to correct me on this too. I think part of the reason why solar physics is so hard is because we can't even see past the photosphere, right? Like, we have nothing to really, it's all theory as to what goes on the inside.
Yeah, I have many classmates who were doing interior stuff, and it's so much fluids, it's so much differential equations and the computer modeling, and it's just, you really have to like math or at least tolerate it.
Yeah.
But yeah, it also just as an aside, it amuses me that the photosphere, like, here's another way to start fights at AAS is technically the sun doesn't have a surface. It's a ball of plasma. It doesn't have a surface the way water has a surface. It's just gas, which, it just becomes more and more diffuse. I have had some researchers come up and say, no, but these are very obvious, because the reason that the photosphere is the surface is because of optics reasons. That's the point where light can actually escape. So like, but it's also kind of arbitrarily chosen. That's where the surface becomes opaque for 500 nanometers. Which happens to be the peak of the blackbody curve. But it's still a somewhat arbitrary choice.
Yeah. Okay.
If you look at it in different wavelengths, the sun looks at various different sizes.
I get, it's funny because I never thought about it like that, but yeah, you're right.
Yeah, I have had. It's great. It's a great thing to use with like grade schoolers because it just really blows their mind.
Yeah.
And then you can also bring Lion King into it in a really nice way. But if you bring up, scientists really like nitpicking. They're so invested in the details that sometimes they can't see past them. The very trees, forest for the trees thing. So they're like, well, but no, but it's a mathematically defined boundary and it has all this stuff. And it's just like, yes, but like, It's a ball of gas. Anyway, people will fight me.
Janelle asked this too because it happens too. So other stars in the solar system do the same thing with like flares and CMEs and stuff. I'm trying to think. I'm like, is there like another star that's like your favorite?
Oh, another star?
Does it like one
That's a good question.
that has like big giant CMEs?
Well, okay, so weirdly enough, yes. So my grad advisor, he kind of straddled the line between solar physicist and stellar astrophysicist. So he was looking at solar flares and stellar flares because, believe it or not, there are papers that are trying, that have to prove that, yes, it's the same phenomenon because it's science. You can't assume anything. And also, basically, if flares are a magnetic phenomena, which, you can't prove anything in science, you can only disprove it. So far, we haven't found any proof to the contrary. If solar flares are a magnetic phenomenon, then any star that has a strong enough magnetic field will flare. The question is whether or not you can observe it. So solar flares in general, create light at every part of the spectrum, but they tend to be very bright in ultraviolet light. So if you have like a blue star, you're not going to see that very well because you just don't have very much of a contrast. So we don't have a lot of literature on flares from yellow stars, for example, like the middle-aged ones, because it's like trying to see a flashlight in front of a floodlight. We can see it on the sun because the sun is right here.
Yeah.
But everything else. So most of stellar flare literature is on N dwarfs, which is nice because that makes up 75% of the galaxy. And so the one that my professor used a lot was AD Leo, which is known as a flare star. And like stellar flares can get up to X200.
Yeah. Nice.
And now you start having questions about habitability, right? Because M dwarfs is 75% of the stellar population. They're much easier to observe exoplanets around. Also, their habitable zone is a lot closer in because they're smaller and cooler. But that also means you're a much bigger target for these X200 solar flares. Are you actually habitable?
Yeah.
It's a very big question. So there's also a lot of questions of, you have an X200 flare coming into your atmosphere and causing photodissociation and photochemistry and all that lovely stuff. Is that causing biological signatures that are not actually from life? There are whole fields of study on that.
Huh.
Yeah, basically, can you make oxygen? They're called abiotic signatures.
Huh. Well, now I have something to Google further.
It's really fun. It's a really interesting question, just how important is a magnetosphere to being habitable?
Yeah. I mean, I just from the small amount of time I've been in this whole world, I think it's quite important. Like, you won't catch me in space anytime soon.
Yeah, so. I have a friend who genuinely wanted to be an astronaut, and I'm like, yeah, you go, girl, but like,
yeah,
no,
but no. Like, I don't want any part of that.
Nope. I mean, I still get nervous on airplanes. I don't need to go higher than that.
Yeah. So, anyway, I think that might have been our last little questions that we had.
Okay.
So yeah, but everybody said thank you for all the chit chat and.
Oh yeah, thanks for the opportunity. I love talking about this stuff.
Yeah, it's always fun doing these because as you can see, we go off on tangents, and sometimes these are really interesting tangents too. So.
Well, yeah, and also just kind of, I really appreciate just kind of as inside how informal this is.
Uh-huh.
And it allows it to really be a conversation because so often science and scientists are kind of put on like, not necessarily a pedestal, but like, this other space. Like the comment that I always get, actually to the point where my entire cohort would make jokes about it and comment on it. If I want to talk to people, like if we're sitting next to somebody on the airplane and they ask, hey, what do you do? If I want to talk to them, I say I'm an astronomer. If I don't want to talk, I say I'm an astrophysicist. Because, like 10 to 1, or like 9, whatever that is, their immediate response will be, "Oh, you must be so smart," and therefore I am not.
Yeah.
And it just kind of it immediately shuts down the conversation. So the ability that this is a conversation and
Yeah.
not just a lecture is really nice.
Yeah, that's what we like it that way too. So that's kind of like, and the people that watch it have seemed to be get a good. They like that too because it is very. It's freeing.
Yeah. Uh-huh.
So
It's a great way to
you
ask
know,
questions.
but I
Yeah.
think
Thanks for the opportunity. I enjoyed it.
yeah, this is fun. So maybe we'll have to have you back sometime. Like if we have something really interesting.
Oh,
going
I'd be
on.
happy to. Maybe if something actually changes and we give better. Maybe we'll see.
Yeah,
Things move so slowly.
like I get it. Well, anyway, I'll let everybody on the stream go, and but yeah. So thanks for coming here, and thanks for talking to us, and thanks for talking to everybody in the chat. I'll appreciate you.
Yes.
So and then we'll be back next week sometime. Actually, we have Scott McIntosh on next week.
Yes, we do.
Oh, really?
Yeah. Speaking
Yes.
of putting a PG-13 rating on things. So we'll leave them with that. But
Yeah, I think that's gonna bump us to at least R rating.
yeah, he's hard to contain, but for good reason. So that's all good. So
Space weather people can be very opinionated. There
Yeah.
have been conferences I've been to where it wasn't quite the words "fight me" in the parking lot, but it got very close.
right, yes. Alrighty. Well, you all have a good night now, and I will end it on the YouTubes.